This instructional video is designed to show you how to calculate binding energy in the context of nuclear reactions. Here we have the mass of sodium-23 in atomic mass units, as well as the mass of the proton and neutron in atomic mass units. And we want to answer the question, how much energy is needed to take a sodium-23 nucleus and separate it into the protons and neutrons. In order to do that, the first step is to write the reaction. And so we have sodium-23 becoming a collection of protons and neutrons. Now, from the reaction balancing, we know that the sum of the mass line for products has to equal our reactants, and the sum for the nuclear charge line for reactants and products also have to be equal. So the only way we get 11 here is if we take 11 protons, and the only way we get 23 here is if we take 12 neutrons. So once we have that, we can determine the mass defect, and the mass defect is just the change in mass going from products to reactants. So we need the mass of products. We're going to do 11 times the mass of the proton and 12 times the mass of the neutron. And then we have to subtract off the mass of our sodium-23. So our mass of products minus mass of reactants will give us the total change in mass in our reaction. And in this case, because we're going from a bound nucleus to the component parts, we're going to see an overall increase in mass. And that's 0.200967 atomic mass units. And so now, once we have the mass defect, all we need to do is convert that mass into energy. And for that, we're going to take the mass, so we take the mass 0.200967 units, and we're going to multiply that by our conversion factor, where 1 atomic mass unit corresponds to 931.5 MeV. And so with this, we find that if we complete this reaction, our delta E is 187.2 MeV. And this corresponds to the amount of energy necessary to be pumped into a nucleus of sodium-23 to break it into protons and neutrons.